of now, we understand how we can design the up counter. Up counter means simply it will start from 0, 1, 2, and then 3, then it will come to the 0 if I'm talking about mode 4 counter. Now, if I'm talking about mode 4 counter, asynchronous word, but the down counter, I just told you only one difference is there. Okay, there is no big differences. If I'm talking about a down counter, in that case, it will start from 3, it will come to 2, then it will come to 1, then it will come to 0, and then again from 0 to 1, this one. So this is the sequence that we are going to follow. Now, if I'm talking about this clock sequences, then how it will follow? Let us try to see. Initially, it will start from 3, 2, 1, 0, then again it will come to 3. So this is the clock count sequence. If we talk about the outputs of both the flip-flops, because see here we have mod 4, so total number of flip-flop requirement will be 2, and the 2 number of outputs will be there. And where if I'm considering A1 is the MSB and A0 is the LSB, so the sequence will be something like this: 1 1 1 0 0 1 and 0 0, and then again it should come to 1 1. Okay. So if it is like this, yeah, so let me go back to the previous slide because that is something important here. Here. This AND gate, what this AND gate was doing? This AND gate was a secondary circuit that needs to change its original sequence. Like if there is no AND gate, NAND gate. If there is no NAND gate, what does it mean? It means that it will complete all the sequences. Like if there is a 2 flip-flops, the total number of sequences will be 4. So 0, 1, 2, 3, then it will come to 0 and so on. But if you are using some additional circuitry, then this may change the number of sequences that the counter will follow. Okay, so the number of sequences that depends on these things. Okay, so let us try to consider those things. So here I have this. If you see here, the changes are here, like A1 is changing from 1 to 0. Sorry, A0 is changing from 1 to 0, and A1 is unchanged. Okay. Similarly, if we talk about this case, in this case, A0 is changing from 0 to 1, and A1 is also changing from 1 to 0, and so on. You can just write it down. Okay, so this is something that you should know. Now, how to design the circuit? Okay, the circuit is something like this. See here, I just told you, clock pulse will be connected to this one of the clock pulse. The T will be connected to logic high. Output I have to take from A0, but the second clock pulse will be controlled with the help of complement of the previous output. Okay, because the previous output was A0 and this is nothing but this is the Q0. So this clock pulse will be controlled with the help of Q0 bar, not the Q0. So the only difference that we can see here, like if I want to make a mod 4 down counter, then I have to control this clock pulse of the second flip-flop with the Q0 bar. And if I have to make the up counter, then this should be connected to this one. So up and down counter is decided from where I am just taking this clock pulse from the previous one. Like if the Q0 is connected to the clock pulse on the next one, then it is fine. And if Q1 bar is connected to the clock pulse, then it will be down counter. So the up and down counter are decided based on the connection of this clock pulse of the next state, either with the Q0 or with the Q0 bar. Okay, and if it is like that, then initially the clock pulse will be like, initially it is reset, and after the first clock pulse, all the flip-flop will be set to logic 1. Okay, 1 1 will be there, and then it will decrease 1 1, then 0 1 or 1 0. Simply A1 is MSB, so 1 0 0 1 and so on. So this is how the timing diagram for this clock pulse will look like. Only difference between up and down counter is the connection from where I'm connecting this clock pulse of the next state. That's it. This is the only difference. Okay, so keep this thing in mind. Let us try to make a up down counter, a single circuit that can act as an up counter as well as the down counter. So how we can make that one? Let us try to see. Suppose if I have a sequence like 0 0, so 0 1 1 0 1 1 and then 0 0. So if the pattern is something like this, like 0 0 to 0 1 1 0 1 1 and so on, something like this, so this kind of sequence we can count is the up counter. Okay, but if the sequence is opposite, like 1 1 to 1 0 1 0 to 0 1, then 0 1 to 0 0, then 0 0 to 1 1, then this we can call it the down counter sequence. Okay, so the up and down counter, a single circuit we can make like up counter as well as the down counter. So this is how we can make it. Now I just told you how much up counter and the down counters are different from each other. Keep those things in mind, and then let us try to see here. I have not connected the next state clock pulse with any of the outputs of the first stage. Now please let me know what kind of arrangement I need to make so that the same circuit can act as an up counter and the down counter. So suppose I have this multiplexer, 2⁻⁴ multiplexer. What these 2⁻⁴ multiplexer do? Based on this control signal, basically it decides which of the input will be transferred to this output. Okay, so this A0 is connected to the I0 and Q0 bar is connected to the I1, and I need this I0 should be transferred if I want to make it up counter. So if S is equal to 0, then it will act as an up counter and the output that should be connected to the clock pulse. So the output is connected to the clock pulse, and then this A0 will be transferred to this clock pulse. So if S is equal to 0, it will act as an up counter. Okay, and if S is equal to 1, then what will happen? This this I1 will be selected, and I1 is connected to the Q0 bar, and in this case, this Q0 bar will be connected to the CP1. Okay, so in this case, it will act as a down counter. So this is the simple thing that you should consider, how you can make it up counter and the down counter based on this multiplexer. So you need one additional hardware, which is the multiplexer, and then you can use the same circuit that can act as a up counter or the down counter. Okay, so we can call them the up down counter, okay, or hybrid counter, which we saw previously. Okay, and again, this is the asynchronous one because the outputs are controlled to connected to the next stage clock pulse. So this is the asynchronous one. Why we are calling it the mod 4? Because the total number of stages are 4 only. So this is the mod 4. So this is the simple circuitry for mod 4 asynchronous up down counter. Asynchronous means ripple counter. We can sometimes you may see the questions are written like the ripple counter. So ripple is nothing but this is the asynchronous one. Okay, so you can either call it as asynchronous or the ripple counter. So both is having same meaning. Okay, so let us try to see how we can make the mode 8 asynchronous up counter. Yeah, mode 8 asynchronous up counter means it will start from 0 0 0 and that will reach up to 1 1 1, and again it will be something like this. And for this purpose we need 3 flip-flops, and simply the output of first one will be connected to the clock of the second one, output of second one will be connected to the clock of the next one, and so on. So this is how we can make the mod 8 counter, and this is how the truth table will timing diagram will look like. I think if you know the mod 4 counter, so you can understand it easily. Okay, so the A0, A1 and A2 will reflect like this. Okay, so similarly you can also make like mod 8 down counter. Okay, so the down counter is also possible. Okay, so the initially after the first clock pulse all will be 1 1 1, and then it will start reducing, something like this. So this is how we can make the modulus 8 asynchronous up counter. Okay. Yeah, here is one example that we should consider. Design a mod 5 up asynchronous counter from the modulus 8 up counter. So I have already modulus 8 up counter, and I want to make it as a modulus 5 up counter. Okay, so how to do that? Okay, and so what it means? It means that the sequence will be 0 0 0 0 0 1 0 1 0 0 1 1 and 1 0 0, and the sequence will be something like this. This is the sequence which this counter is going to follow. Okay, and then it will start repeating the things. Now let us try to see how the circuit will look like. See here, because after this stage 1 0 0, okay, the output should reach to grounded one. So here what I did, I need one NAND gate. What I did in the previously, right? So in this NAND gate, what I have to do, I have to check like this is the MSB, which indicates like A2, okay, A2, A1, and A0. This is the structure, okay. And if I have to make like 1 0 0, so see here, this is the A2. A2 has been controlled with the Q2, that becomes 1. So this is how it is connected. A1 is 0, so I will the second input will be like Q1 bar, that will be connected to the NAND gate. And similarly this one, like third one is 0 0 0 is there. So because see here, one important thing that we should consider, sorry, I made a mistake here. So these all are the valid states, right? The next state could be 1 0 1. 1 0 1 is invalid state, and once this is coming, this should not come, this should reset to 0 0 0. Okay, so see here, this is the Q2 is nothing but this is the A2, so this will come directly here. Q1 bar, because the next digit is 0, so the Q1 bar will come to this point. And then A1 is nothing, A0 is nothing but this is the 1, so this will reset. So once this output 1 0 1 will come out, it will start resetting the things. Okay, because this is 0, so this will become 1, so all the inputs will be 1 1 1, and accordingly it will give 0 to make it preset. Okay, so this is how I can make the mod 5 counter based on mod 8 counter. So what is the learning here? The learning is, first I have to check which of the state is not needed. Okay, so because initially 1 0 1 was there, and I don't need 1 0 1. If I don't need 1 0 1, just try to see it. 1, which is the MSB, this is the medium one, and this is the LSB, and accordingly just connect this one, and then that will become the modulus 5 counter. So this is how it is, how simple the modulus 5 counter design is. Okay, and accordingly the truth table will look like this. I just told you this is nothing but this is the glitch which we can observe. Okay, and accordingly it will change the state, and output is same like that what we already studied before. So this is all about the problem. If you have any problem on this, how we got these things, so this is easily very, very easy. Like I have to find which of the state is not required, then I have to make the logic accordingly. That's it. This is the simple thing that you have to do. Okay, so this is the thing. Next thing is like I'm just giving you the 2 tutorial questions, like draw a sequence and the timing diagram of the given counter circuit. And the second thing is design a mod 3 down asynchronous counter from mod 8 down asynchronous counter. So this is what you have to make. So these two are the homework that you have to do that. So this is all about the today's lecture. The other things will continue. Like see, as of now, by just seeing the state diagram, we just drawn the circuit, but how exactly we find? Okay, see, suppose I have more number of variables, so it is not possible like just see the states. Suppose I have a 10,000 states, so it will be very difficult to find which of the state is not available. So in that case, the designing the proper position, the proper procedure need to be followed to design the counter. Okay, so in the next lecture we will talk about what exactly procedure that we have to follow to make any particular kind of counters. Okay, so as of now we have studied how we can make the mode 4 up counter, considering the asynchronous one. So what we can see, like for mode 4, we need total 2 number of flip-flops. Okay, we know that the mode M is defined as that should be less than or is equal to 2 to the power n. Okay, so the number where n is the number of flip-flop requirement, and M, which is the possible mode that we can design out of this one. So suppose I have a 2 flip-flops, so the total possibilities could be like 4. Okay, so the I can design the let's see, if n is equal to 2, in that case m will be 4. What does it mean? It means that with the help of 2 number of flip-flops, with the help of 2 flip-flops, I can design mode 4 flip-flop. Even less than that is also possible. Mode 3 flip-flop is also possible. Mode 2 flip-flop is also possible. Mode 1 flip-flop is also possible. So the highest possible mode that is possible with the n flip-flop will be the 2 to the power n. Okay, so this is the important thing that you should know, and this is really very key point that you should remember. Okay, so suppose I have to make mode 8 counter. Okay, so we know this formula, m that is less than is equal to 2 to the power n, and if m is equal to 8, what it means, the n is coming around 3. Okay, so what does it mean? It means that we require 3 number of flip-flops to design the counter. Now one thing we got, like we need three flip-flops, because I am making the asynchronous counter. And if asynchronous counter means what? The output of first flip-flop that should be connected to the clock of the second flip-flop, and the output of the second flip-flop should be connected to the clock of the third flip-flop. Okay, so the asynchronous means is the if the output of the first stage is connected is treating as a clock for the next one, then this is the asynchronous one. Okay, and up counter means, like, because I am designing the mode 8 counter and total number of flip-flops will be 3, so 3-bit possibilities are there. So total number of possibilities that could be like, that is from 0 0 0 to 1 1 1. So these are the all possible counts that we can design with the help of mode 8 counter. Okay, so let us try to consider in more detail. Yeah, so these all are the possible stages, possible values which are possible, which that can exist. So that will start from 0 0 0 0 0 1 and so on, and that will reach up to the 1 1 1. And once it reaches to the 1 1 1, that will again come back to the 0 0 0 and so on. So this is how the clock will keep on repeating. Okay, now as I already told you, we require 3 number of flip-flop, and the output of the first flip-flop ff0, that will be connected to the clock of the second flip-flop, and the output of the second flip-flop will be connected to the clock of the third flip-flop. So this is how it simply looks like. So this is the simple structure. Similarly, if I have to design mode 16 counter, so mode 16 counter, what I will have one more flip-flop after ff2. Okay, and this A2 will be connected to the clock of that the fourth flip-flop, and this is how we can increase the mode. Okay, so this is the simple structure. Now one very important thing is, because these all the flip-flops are the negative age triggered. If you can recall here, all the flip-flops are negative age triggered. So the change in the state is only possible if the falling pulse is there. So during the falling pulse, the changes are possible. Okay, so suppose I have a clock pulse. Yeah, so suppose this is the clock pulse CP. So this A0 will be reflected. It will change its state only when the clock has the falling edge. So this is the falling edge for the clock. So at this time, A0 will change its state from, initially it was 0, so 0 0, then it will come to the 1. Okay, and it will maintain the same logic unless it will not get the next falling pulse. Okay, so the next falling pulse will be here, then again it will change its state from high to low and low to high and so on. Okay, now if you can recall, if you can see here, this A2 is acting as a clock pulse for this FF1. So this FF1 will change its state when there will be the falling edge on A0. Okay, so the A0 is here. This is the rising pulse. Now this is the falling pulse. So this falling pulse will act as a clock for the FF1. So A1 will change its state only when there is a falling pulse at the A0. Okay, so initially A1 was 0. Now it will change its state when there is a falling pulse at A0. So this is how it is going to change. And similarly, this FF2 will be triggered when A1 has the falling edge. So A1 has a falling edge at this time. At this time instant, A1 has a falling state. So initially the A2 will be maintained at logic low until there is no falling edge at the A1s. Okay, so once A1 is having the falling edge, then A2 will change its state and so on. So now if we can recall at each stage, initially the clock frequency, this one was the time period for the clock. Okay, this one was the time period T. Okay, if you can see at the A0, the time period has been increased by double, or the frequency has been reduced by half. Okay, so the frequency is reduced or the time period is increased by double. Similarly for A1, again it becomes the 40. For A2, it will become the 80 and so on. So as we keep on increasing the number of stages, the frequency is getting half at each stage. Okay, so suppose I have a clock frequency having 1 megahertz at the input side, and if I have a 3 stages, so after the first stage I will get here like 500 kilohertz, here I will get 250 kilohertz and so on. So the next stage that will pass through, that will be like 125 kilohertz and so on. So whatever the frequency I need, so where I can use this kind of circuits, I can use this kind of circuit. Suppose in a particular circuit I need 3 different clock signals, okay, which are the multiple of 2. Okay, so in that case, what I will do, I will provide one clock frequency, let us assume 1 megahertz. Then if I will pass it through a flip-flop, then the frequency will be half, like 500 kilohertz kind of signal can also be utilized. Okay, so whatever the signal over here is, this is nothing but this is again a signal that having the frequency of 500 kilohertz. Okay, similarly, if again I pass through a flip-flop, then it will be half and then so on. So the multiple number of frequency can be considered. We don't need a different frequency sources. Okay, we need only one frequency source to get the different variant of the frequencies. Okay, but yes, the limitation is like we can only get the multiple of 2 frequencies only. If I need like 400 kilohertz, so this 400 kilohertz is not possible from here. So I need to use some other kind of structure. Okay, so this is all about how we can make the mod 8 counter with the help of this one. Okay, the whole points are clear. So if this is clear, then let us move ahead. Something like, let us take some example and then try to solve it, how it could be done. Okay. As of now, we just understand how the mod 8 counter up counter looks like, asynchronous up counter looks like. In the previous slide, just we saw. Okay. Now, what I have to do, I have to design a mod 5 up asynchronous counter from mod 8 counter. Okay. If I'm considering the mod 5, what it means, the total valid states are 000, 001, 010, 011 and 100. Then after whatever the value like 101, 110 and 111, these are not valid state. Okay, so these are not the valid state, only the valid states are this one. Okay, so the sequence will be something like this. Okay, these are the sequences and the unvalid like not valid, these 3 stages are not valid. Now let us try to see. Yeah, this is the diagram which we have which we saw in the previous slide, and we saw like this is simply a mode 8 counter. Okay, the output of the first stage that is connected to the clock, and the output of the second one is connected to the clock of the third one, and so on. Okay, so this diagram is simply a mode 8 counter. Now the thing is, the total valid is still up to this 100 is valid. And what is our objective? Mode 5 counter means what? Once it reaches to 100, the next state should be 000. Okay, but if there is no clear or something, the next stage should be 101. But because I want to make it mode 5 counter, the next stage should be 010. So when 100 comes, it should clear this counter. Let me repeat it again what I'm saying. Okay, let me change the color so that you will. Okay, so what we know, like 100 is the valid state. Okay, 100 is the valid state, and what I want after this 100, I need to clear it at 000. Okay, so to reset or to clear the data on the flip flop, the clear pulse is the important signal. Okay, so when the next stage comes, 101 comes, the clear pulse must be activated. Okay, so 101 comes, then the clear pulse must be activated. What it means? If this Q0 is 1, Q1 is 0, and Q2 is 1, in this case, the clock, this clear pulse must be activated. Okay, so clear pulse must be activated. So to activate, what I can do, I can simply just connect something like this. Yeah, so the Y that I need here is equal to here. Let us try to see here. Let us assume this is the A0, this is A1, and let us assume this is the A2. These three are the outputs. Okay, A0, A1, and A2. So what I need, Y, which is required to clear this flip flop or this counter, is nothing but this is A2 into A1 bar into A0 to the whole complement. How it is so? Let us try to see. When 1, 0, 1 will be there, the Y, this should be 0. Okay, Y should be 0. So simply let us try to see. A2 is 1, A1 is 0, and I need the complement. So this is like 1 into 1 into 1. Okay, so 1, 1, 1, and that will, and the complement of this, that will give you the 0. So the Y is 0 if I need to use these kind of control signal like A2, A1 bar, A0, and whole complement. So if it is like that, the circuit will be cleared, and from 100 to it will move to the 000. Okay, so what kind of circuit I need for this purpose? I need the circuit like, see here, I am just NANDing it. Like, so if you see here, A2, A1 bar, A0, these are the AND, and the complement is the NAND. And what I need, the complement of A2, A1. Okay, so let us try to use one circuit that can solve this purpose. Okay, so let us try to design it. So I need one NAND gate that should be connected to this Y. One of the signals should be connected to the A0. Okay, one of the signal that should be connected to A2, and the third one is A1 complement is needed. So what I can do, I can either use one inverter and then connect to this one. So this is also one of the possibility. The second possibility could be like, because I have to connect Q1 and Q1 bar is already available. So why I need this inverter? I don't need to use one more inverter. So simply what I can do, if somehow I can connect this Q1 bar with this one, so this is nothing but this is the A1 bar. Okay, so this whole circuitry will act as a mod 5 counter. Okay, so if we have any doubt at this stage, you can ask the question how I come to this particular circuit, like how this circuit is required to clear this circuit or this counter. So if you have any doubt, you can ask the question. Okay, so if there is no doubt, we can move ahead. Okay, yeah, so now the timing diagram will look like this one. So initially it will start counting from 0 0 0. It will go to the 0 0 1 0 1 0 0 1 1 1 0 0 like and 1 0 0. This is fine. And once it reaches to the next clock pulse, okay, that will clear. Yeah, again I just told you how, because it will wait to come like 1 0 1, and once this reach, this will clear. So for some instant of time, this 101 will also be there, that will be in existence for some period of time. Okay, so that may also required for this purpose. Okay. So this is how the timing diagram will look like. So when this signal will come, this one, okay, this one, and this one, and so if all these are coming at this case, it will be reset to 0. Okay, so the counter will be reset to 0. Okay. So this is the important thing that we should consider. Now, yeah, here we have some tutorial questions like draw the sequence in the timing diagram of the given counter. Okay, so whatever the circuit I have here, I have connected like Q0 with the clock, Q1 bar with the clock, and I'm taking the Q2 output. So A0, A1, and A2, just there we are taking from Q1, Q0, Q1, Q2, but the first output that is connected to the clock pulse, but in the second one I have just connected the complement of this output to the clock pulse. So accordingly the timing diagram and the sequence will be changed. Okay, so check it out, what sequence it is following and what is the timing diagram. Just we have to check it out how it is getting activated. Okay, the next problem is design a mod 3 down asynchronous counter from mod 8 down asynchronous counter. Okay, just like we did in the previous slide, we just designed mod 5 counter with the help of mod 8. Similarly, you can design mod 3 counter with the help of mod 8 counter. Okay, so this is the homework. Just please do it at home.